find out what's the gain of this circuit, okay? So on the left, again, this is the common gate amplifier. We have the source, we have the drain, we have the gate. And as what we said before, all we need to do first is to substitute the small signal model, GM, VGS, to the circuit, VGS. Is this okay? And then we'll start computing the circuit, right? For the drain, we care about the V out, but then I am going to put the RD here, which probably is wrong. I make a mistake. Where should the RD end up at? Should be going to ground, and I kind of connected it to the source. Unfortunately, the source is not grounded. It is V in, right? So I make a mistake here. I should just remove this one and connect this to ground, right? I cannot connect it to the source. In common source amplifier, connect to the source is okay because that was source, right? How about the gate? What do I do? DC voltage, and it is grounded also, right? Because it's DC. You need to ground all the DC voltage, open all the DC current. Any questions? And I ignore the channel length modulation. I remove the resistor. Out, right? So good. So all my goal is to find out what is the relationship between V out and V in, and again, KCL. Right? So how do I do the KCL? Up to you. I will do a loop like this. The direction is very important. So IRD equal to GM VGS. What is IRD again? 0 minus V out DYRD. Yeah, be very careful. Times GM. What is VGS? Again, break it down. VG minus VS, which is 0 minus VS is V in, right? So you can see that V in divided by V out is just GM RD. Very easy task this time, right? That's it. But I want to emphasize one thing. It's not exactly the same as the common source because here we did not consider the channel length modulation. If you consider the channel length modulation for common source, it is negative GM RD parallel R0, right? This is the common source. But if you include the channel length modulation, you actually get this gain. GM plus 1 over R0 times RD parallel R0. So it's different. It's not exactly the same. Only when the channel length modulation is ignored, they will be the same, right? Just a reminder, a note. Yes. Thank you. Yeah, thank you. I have a typo. This should be V out over V in as the gain, right? Not the V in over V out. Thank you. Yeah. So you're paying attention. Is this okay? Well, I just want to keep showing you that all this are easy to you. All you need to do is just to think carefully and do it step by step. And if you don't make mistake, the worst case is just that you cannot solve the equation. You won't get the wrong answer if you don't make mistake. Do it step by step. Same in the future when you run into a big circuit. The worst case just you don't know how to solve it, but you don't get the wrong answer. Okay? And the best case, of course, solve it. I think you can do it most of the time. Okay? So this is the small signal of the common source common gate, right? The gain, GMRD. And I hope you start having a table to write down the gain of different circuits. And you will be at your gauge, right? Like the game. Take it out anytime. It's a dictionary for you to use in different situations. Now, we want to know about the input impedance of this circuit. Okay? On the left, again, I try this intuitive view. Can be confusing, but if you understand, that would be very useful for you to work on things with inspection. What is the input impedance? Again, the first thing I need to know is the definition. What's the definition of input impedance? V in over I in when I out equal to 0, right? We are not loading anything. There's no loading, so there's no I out. So we fulfill this condition already, right? So let's try to see what happened. Okay, I try to do V in increase by delta X, delta V, right? Just exactly what you're doing on the bench, test bench, or as an electron. I increase the voltage by delta V. Then I want to know how much the current will go in. Remember, this is the input, right? Ix is the I in. Okay. So how much how much current will change? Well, when V in increase by delta V, again, is the same as what we discussed earlier. Vs increased by delta V because it's Vs. And as we discussed earlier, Vgs is going to reduce by delta V. Is this okay? Yeah, so we're just repeating what we said earlier. V in increase, right? And then Vs increase, then Vgs reduce. Make sense? And then we go to the transconductance. So as we said last time, because of this, ID, this is ID, is going to what? Reduce by Gm delta V, but because Gm delta V. So actually I don't need to put the absolute value here. I was kind of right, because delta V is positive, right? So you reduce by Gm delta V. Is this okay? But what is the relationship between ID and Ix? Look at the graph. What is the relationship between I in and Ix? Based on what I draw. They're opposing. Mathematically, just negative to each other, right? So Ix, so if ID reduced by Gm delta V, what happened to Ix? Increased by Gm delta V. Right? So the input impedance is just equal to the delta Ix? No. What should that be? Delta V in divided by delta I in, right? Which is delta Ix. So what is that? Delta I in is what? Delta V. How about delta Ix I in? Gm delta V. So what is the input impedance? 1 over Gm. And then you think about that. Does that make sense? Oh yeah. Isn't that we have been saying that if you look into the source of the transistor, the input impedance is 1 over Gm? Remember? We solved that already last time. But your drain does not have to be grounded. You can go through an RD and connect it to VDD. It's still 1 over Gm. If you don't have channel length modulation. Okay. So now let's go back to the resistance question. We say that if in this case, when we look down, we say that the resistance is not R0 plus Rs, it's something very bulky, right? Because if we solve the small signal, we will get this. Now, similarly, look at this. What is the input impedance to here? This one is equal to 1 over Gm, not 1 over Gm plus Rd. Okay? Why is that? Because if you solve the small signal, you get that. It's just like I'm pushing the table, because whenever push, a student just want to do something opposite to me. Okay, let's say I'm blind, I cannot see, I don't know someone is pushing against me, right? This is just the law, the physics. So you do not say that this is 1 over Gm plus RD, right? But however, this is only the case when there's no channel length modulation. When there's channel length modulation, that is more complicated. You need and you can solve the equation. So in your assignment 2, there are a few places that you need to solve the equation. Okay, solve the small signal, because you cannot map it. Okay. So first of all, is it okay for this intuitive view? That how you get 1 over Gm? So if it's okay, then let's go to the small signal to verify what we're talking about, right? So again, I draw the small signal circuit. And then I have V in. And I what care about is I in, right? It's getting difficult to see. This is V in. I have current, that is I in. I ignore the channel length. I ignore the channel length modulation. The gate is grounded, right? This is VGS, so this is GM-VGS. And then I don't have channel length modulation. I have the RD connects directly to ground, right? Again, why it is grounded, the RD? Isn't that is VDD? Anyone? You answered me many times already, you guys. Because it's AC grounded, right? Okay. Okay, so let's start this. And again, I'm going to use KCL, KVL. But this is very simple, turn out. KCL. What is KCL? I in equals to negative GMVGS. Do you agree? I in is going up, GMVGS going down. They must be negative to each other. Or I say I in plus GMVGS equal to 0. KCL. Right? And what is VGS? Thank you. VG minus VS. What is VG? What is VS? V in. Turn out this is also very easy. So R in equals to V in divided by I in equals to 1 over Gm. Do you see that? Huh? So very low impedance. How about RD? My proof show you that even RD is hanging there, it's not going to affect my R in just because of the physics. Right? Whether you're large or small, I always have GMVGS equal to negative I in. But if I have channel length modulation, I put an R0 here, then it will be different. Because now the KCL is R in equal to negative GMVGS plus the current going through the R out. But the current going through the R out depends on the potential here. And now the potential here depends on the value of RD. Right? Because whenever I have a potential here, then I will have a different current going through RD. Then the RD has a role in the input impedance, right? And what is that? If I include the channel length modulation, this is the input impedance. It's R0 plus RD divided by 1 plus GM R0. Okay, you can derive it, and you need to keep this because we need this for the assignment or even exam. Okay, I don't derive it because it's lengthy. I want to save the time. If R0 is very large, you see that I can ignore 1. I can ignore RD because R0 plus RD is dominated by R0. It becomes R0. the denominator becomes GM R0. Then R0 got cancelled. Again, it's 1 over GM, which makes sense again. Is there any questions? Yeah, if you have question, ask now because it's a part of the midterm or it is related to other part of the material, right? So I can spend time to explain more, including how you come up with the small signal circuit, how you solve it or whatever. Any questions? RO plus RD, sorry for my writing. Say again, I cannot hear the last. What equal to RD? Oh, you're talking about the circuit, right? Yeah. If you have channel length modulation, then you will add the R0 and then connect it to here. Not to the ground, so you cannot say RD parallel R0, right? Do I answer your question? Thank you. I'm going to erase this, right, so people won't get confused. Okay, good. So low input impedance, why we need that? Because, for example, sometimes you use it in a transmission line, you need 50 ohm, right? So you need to have this input impedance of 50 ohm, right? Last time some people asked about impedance matching, right? So that's why this is very useful. Instead of going into the gate, now you have the gain, GNRD, just like common source amplifier, right? Your transmission line, the signal reduce, and then you amplify it. It's just like a repeater, like the cable, optical fiber, right? Okay. How about the output impedance of this circuit? So I would like to go through this by almost inspection, but it's a rigorous one. So on the left, we have this common source, common gate amplifier. Again, this is the gate, this is the drain, this is the source. Input goes into the source, and this is the output, right? So I just flip it a little bit in order to match this drawing. Again, I just put the V out here, right? This is V in, right? This is source, this is drain, and this is the gate. Is this okay? Right? I just connect it. Now, I can draw the small signal model like this. I can draw it like this. And I'm going to draw it on another side. Right? And then this is going to be I hope this is still recording. Let me stop it because sometimes it will mess up when this happens. Right, so this is grounded, correct? No, this is not grounded. What should be the gate? What should it do? Or it should be grounded or not? What's the output impedance? How do you find the output impedance? Output impedance. I'm finding the output impedance. So you apply the, so here I completely mess up, right? Even this is wrong. Let's redo. What is output impedance? I did it wrong. R out equals to V out divided by I out. V equals 0, right? So let's do this. Where's V out? This is V out. And I apply try to find I out. when V in equal to 0? Where's V in? No. Source. Let me just... Source is grounded, right? I also ground the gate. Correct? Because this is a constant voltage. Then you try to solve the small signal model like this. But I don't want to do that. I want to do inspection. I still keep the drawing here, M1. But I do ground the gate, ground the source. Do you see this? Because the V in is grounded, the gate is grounded, AC ground. Right? I keep it. I emphasize that I have R out here. Then it means this transistor only has GM. And basically, this whole thing is just drawing this one. This whole thing here is this whole thing here. Yeah. But because I'm confident, I think I grew up already. I don't want to draw the whole thing because I feel that I know what's inside. I just draw this. Okay. And then I even ground the VDD because I know I'm doing AC. But if you give this circuit to anyone who just studying electrical engineer, they will say, what? Your circuit works by grounding everything? You know this is not the case because we are doing AC analysis. These are AC ground. In our mind, we already know that we have DC bias this transistor so that it is at saturation. We know there is a DC current, a huge current going through, biasing it also, right? But now we're just looking at the AC. And if we are not comfortable with this, we can draw this circuit. No problem, right? And definitely here I need to also draw the RD. I also have the RD. I did not draw it, right, for the full circuit. But this is not what I want to discuss. Now look at this. As an electron, you go in, right? What do you see? The question is, what resistance preventing you from going to the ground? Very good, right? You just say it. Or there's a resistor. I can go to the ground through the RD. There is one resistor. But I also can go straight forward, right? Definitely, it is RD parallel R out 1. That is my R out, right? Whether you know what is R1 doesn't matter. The point is you do see that it's parallel, right? So I keep walking. What is the resistance I see when of R out 1? Then you see this whole thing, which is just a transistor. Although we draw the R out here, but this is just whole thing as a transistor. The gate is grounded, the source is grounded. So what is the impedance when you look into the drain? A transistor with the gate and the source grounded. Into the drain. You look into the drain, but the source and gate are grounded. What is the resistance? R0. And done. I don't need to solve this complicated circuit. Is this okay? This R0 is just like what we discussed in the common source earlier. We keep talking about this R0 going down, right? Remember? Where the gate and source are grounded. You cannot do that for common source with degeneration because the source is not grounded. And we solve the small signal, you get this one. Okay? So I don't need to do anything. I get RD parallel R0 already. Any questions? Now we